Hello, we are Kirsten, Tejas, Andrew, and Kaya, also known as Team ASCII 32. This semester's 2110 competition, One Giant Leap, involved designing an autonomous device capable of consistently scoring the maximum number of points per round. There were 4 main ways to score points and win the competition: clearing foam rocks in the lunar module landing zone, preserving the location of the lunar module, placing a flag, and egressing from the lunar ridge. All tasks were to be completed in 40 seconds. The competition was scored using a point system with the breakdown as follows. Successfully activating the machine was worth 10 points. Fully clearing all 3 rocks in the Sea of Tranquility while preserving the location of the lunar module was worth 60 points. Successfully placing the flag in Zone 1 was worth 44 points. And egressing from the lunar ridge doubled the score obtained by placing the flag. Teams received a 14-point deduction per sensor decoy in their zone, but could not be deducted more than 42 points in total. If no decoys were placed in your zone, the highest amount of points a team could obtain was 200. The competition was completed on a 7 by 7 foot track with a 30 by 30 inch starting zone. The initial state of the machine had to fit within a 1.5 by 1 by 2 foot volume and had to be activated using banana plugs powered by the track. The machine's power sources were limited to components in the mechatronics kit, which consisted of 2 DC motors, 2 solenoids, and a pneumatic actuator. 5 mousetraps and 5 rubber bands were also allowed, and the total cost of the machine could not exceed $100 beyond what was provided in the mechatronics kit.
The House of Quality highlights 2 very important customer requirements that will result in disqualification if not met: no track damage and starts and stops at rests. Of the major tasks, clear rocks was weighted most heavily due to the large amount of points and how easily obtainable it was, and that it had no dependence on other teams' performance. Another major takeaway of the House of Quality was the importance of distance reached, which was due to its dependence on fulfilling all major tasks, which combined the majority of all total possible points. The most challenging specification to achieve is initial volume. This is because the design would have to reach more than 41 inches to the center of the dome and a height higher than the initial volume. This means the reaching would have to both overcome gravity and have more than one simple motion for the distance. The target points attempted are 10 for activation, 60 for the rocks and lunar module, placing all 3 decoys to lower an opponent's score by 42, and placing the flag in Zone 2 for 22 points and 22 for egressing, leading to a final points of 114.
In the function tree, the functions reach rocks, reach lunar ridge, and reach dome were all determined to be some of the most challenging. Despite this, they could be combined such that one subsystem could complete them all. Identify zones was another difficult task due to the quickness of the ridge's revolution and the small tangible differences in the zone identifiers themselves. Furthermore, this function is critical to the success of the rest of the deploy sensor decoys subfunctions, adding more importance to it.
For this competition, our main design objectives were stability and reliability. To ensure this, we focused on incorporating mechanical systems that we could easily test and perfect instead of electrical systems that were more likely to malfunction. The majority of our subsystems consist of simple mechanical components such as utilizing a wheel at the end of the joy slides to stabilize the machine against the rotating lunar ridge, and using a mousetrap to power the flag arm instead of a motor or another sensor, and a lever system used to deploy not only the joy slides but also to deploy the sensors. By designing simple and reliable systems, we were able to produce a functional and consistent final product. Our final design, Slide Rule, is made up of 4 main subsystems that score an average of 114 points. At the start of each round, the system is activated by a lever located at the back of the robot. The MyRio is programmed to release the actuator that will extend it upwards, pushing the lever down and releasing the joy slides. The 2 connecting sets of joy slides mounted onto the robot base at a downward angle will then extend towards the rotating lunar ridge due to gravity. This motion comes to a stop once the wheel at the end of the joy slides comes into contact with the lunar ridge. This wheel is a significant part of the design because it accurately and consistently locates the lunar ridge and provides a reference point for deploying the sensor decoys and flags without moving the robot itself. Once fully extended, the rock clearing subsystem is activated. Using a specifically designed curved arm, the motor mounted onto the joy slides rotates the arm 360 degrees for 8 seconds, effectively clearing all of the rocks while avoiding the lunar module. Simultaneously, the sensor decoy subsystem is also activated by the beacons protruding from the lunar ridge. Again, relying on a mechanical solution, the triggering mechanism is a swinging arm system with two settings that account for the different zones on the track. Depending on the team's specific starting zone on the track, the sensor decoy subsystem can be set to deploy on either the top two beacons, sending beacons into the yellow or white zone, or the bottom two beacons, sending decoys into the black or blue zone. Upon the start of each round, one of the two flaps will be extended, supporting the small arm holding back the decoys on the machine. Once extended to the lunar ridge, a rotating beacon will push the flap back and release the decoys into the zone. The last subsystem to activate is the flag. Specifically programmed on the MyRio, the arm release is delayed in order to optimize flag placement. By waiting, we minimize the chance of other teams knocking our flag out of the way. This subsystem also incorporates mechanical aspects in that the arm's motion is powered by a mousetrap. The end of the arm is held in place by a solenoid until it is activated, when the arm will release towards the lunar dome. The placement and the angle of the arm ensures that the flag will consistently land in Zone 1 or Zone 2 on the dome. Shortly after the flag is placed, the robot will egress from the lunar ridge through a string and motor system. The string is attached to the robot's base and to the flag arm and will remove it from the lunar ridge. Overall, this design was the most effective and consistent combination of mechanisms that successfully completed all of the tasks.
The morphological chart, shown here in parts, displays the designs chosen for the final design, slide rule, boxed in yellow. The designs chosen for the two alternate designs, Edward's scissor arm and Mario's cart, are outlined in light blue and green respectively. Additionally, the challenging subfunctions identified earlier are highlighted in red. Edward Scissor Arm's design revolves primarily around its extending scissor arm, which houses both the sensor decoy and flag task subassemblies. Once extended, the IR sensor will detect the zone, causing a solenoid to retract and the decoys to fall. Simultaneously, the mousetrap will trigger via a string and motor and place the flag on the dome. While this happens, the rock arm will be released via the same string and knock two rocks out of the zone. The driving principle behind Mario's cart is its wheel design powered by a motor and pulley system. This will propel the device forward, allowing the angled front pieces to push the outer rocks away. Once the device has reached the lunar ridge, the long arm switch will detect the desired zone, deploying the sensor decoys from the decoy holder. A motor will propel the flag arm to the center of the dome at the same time. Before the drive motor reverses direction, a solenoid will retract to drop the third rock wall down, which will displace the third rock during aggression.
A third-level evaluation matrix was created in order to compare and contrast the features of the design concepts. Slide rule was chosen because it scored higher than both other designs in many requirements, accuracy being an example. It also scored consistently high in the task-related requirements, which were weighted heavily due to their involvement with scoring points and winning the competition. The only requirement in which slide rule had below a 3 on a 0 to 4 scale was inexpensive. This was due to the cost of the drawer sides, costing approximately $40 total.
Other than the first round, the device performed well, allowing for the advancement to the fourth round. This placement is likely due to the rock and lunar module tasks, which scored very consistently. In the first round, judging interference meant that our device did not deploy, and the device was awarded only the points for deploying and leaving the lunar module untouched. In the second round, the device deployed correctly, and all the subsystems worked as designed. A stray, knocked-over flag interfered with the device's flag placement, but the target score was still achieved. In the third round, the device performed as expected again, with the exception of the flag arm planting the flag in Zone 3 instead of Zone 2. In the fourth round, the rock clearing and sensor deployment systems failed to activate properly, leading to a lower score and placement, and thus elimination from the final competition.
We learned a lot throughout the design process, especially the importance of testing. In the end, the robot was able to accomplish all the tasks we initially attempted. However, it suffered from a couple problems. First, many mechanisms were prone to human error, like the sensor decoy stopper, which wouldn't fall if decoys weren't placed loosely enough. Here, we had just had to have the angle steeper. Another problem was in round 4, when the rock arm got stuck on the lunar ridge. We could have just made the rubber band looser so it could bend more easily. Advice to future victims of 2110 would be 1. Make boxing easy. The last thing you want is to be struggling during competition. 2. Don't assume anything will work until you test them. And 3. Test activation thoroughly. We learned this the hard way, but it always sucks to get 0 points over something so simple.